10 for the exam? Chapter 4? Yeah, that's what I would recommend. What did you say over here? Projectile motion. Okay, we'll do both then. So let's spend a little time on chapter 4. So this is fall 18 exam. Fall 18 exam. I worked this the other day. Let's look at number 20. I'm not going to use clickers today. I just want to get through as much as we can. So as you know, with the test, a good way to practice is to go through and practice all on your own. Those videos are really great, I think, for some things, but they're not good for practice. That I would print out the exams or do it on your tablet or just do it on scratch paper and work through an entire exam all by yourself without any help, and then just see how you did. See what kind of grade you make. If you make a 95%, then you're probably done. You're ready for Friday. But if you're making a 70 or 80 or a 60, then you need to spend more time. You're going to see chapter 3 and chapter 4. It's about even between those two chapters. You'll see, well, this is a one-dimensional problem. No, this is a two-dimensional problem. You'll see about 4 or 5 two-dimensional problems. So let's look at this. All these problems are exactly the same process. 1, you draw the vectors. 2, you resolve the vectors, though in this case we don't need to do that. 3, you apply Newton's second law. And then 4, you solve. You'll always have those steps. So first, let's draw the vectors that we have here. I already have one force that's drawn. I have this object. I'm trying to keep it on the wall, so I'm pushing against the wall. If I don't push hard enough, then it's going to drop because the frictional force won't be enough. So I have that force. I have the weight pulling down, Fw. I have the frictional force. That's going to be Fs. And then I have another force right here. That's my normal force. I like to draw this on a coordinate system. Just helps me to think about this in a more organized way. So I'm going to do that over here. Fs in this direction, Fw in this direction, F, and then Fn. So those are my 4 forces. And what I'm looking for is this force right here. And I know that that force has to equal Fn, because this is a static situation. In a static situation, the sum of the forces in the x and the y will be 0. That's particular to this problem because it's not moving and it's not accelerating. So because of that, I can say that F equals Fn, and I can say that Fs equals Fw. If my static frictional force isn't as big as the weight, it's not going to be a big enough force to hold up this object. So I need to find out what is the normal force, and then I'll know what is this. Now, fortunately, I know that the normal force is related to the frictional force by this relationship. So if I can find out what is the static frictional force, and if I know what mu is, which I do, it's in the problem, then I can figure out the normal force. So this is going to be our attack. I'll say that Fs is equal to Fw. That's equal to m times g, or 2 times 10. The mass is up here. It's 2 kilograms. Now, that's equal to 20. So Fs is also equal to mu times the normal force. So that means that 20 newtons is equal to mu, which is 0.1 times the normal force. That means that my normal force has to be 20 divided by 0.1, or 200 newtons. So since the normal force is 200 and the force is equal to the normal force, the answer is going to be E. That's a good problem. You'll see some variation of that, I'm pretty sure, on Friday. It's an easier two-dimensional problem because you don't have to resolve the vectors into their x and y components. So it's just made a little simpler, but it's also a little more complicated just because of the way we're thinking about friction is different than we do in other problems. Oh, 21. I like 21 too. I have this object that's 20 kilograms, and I apply a force of 140 newtons. Now, usually, if I have this 140 newton force applied to a 20 kilogram object, the acceleration that I would get would be 7 meters per second squared. But this one only accelerates at 5 meters per second squared. That means that I have a force that's holding it back. So if I draw, resolve, apply Newton's second law, solve the equations, if I draw the forces, then I'll have 140 newtons in this direction. I have a frictional force in this direction, Fk. I have a normal force, and I have a weight. This problem looks a lot like the problem that we saw in the previous one. It's just the forces are sort of rotated around. I want to know what is the coefficient of kinetic friction. I know that Fk is equal to mu k times the normal force. That means that mu k is equal to Fk divided by Fn. It's the ratio of those two forces. If you're in the work and energy lab, that's how you find the coefficient of kinetic friction, is by taking the ratio of the kinetic friction and the normal force. You might look at this and say, well, I can figure out the normal force pretty readily because I know that there's zero acceleration in this direction, so the normal force has to equal the weight. Remember, that's not always true, but it's true in this case where I only have those two forces in the y direction. The way that I do that, step 3, I would say the sum of the forces in the y direction is equal to 0. That is Fn minus Fw equals 0. So Fn equals Fw, which is equal to a 20 kilogram times 10, or 200 newtons. So I know that this is going to be 200 in that ratio. Now I need to find out what is Fk. Well, I have Fk right here. You might be inclined to say that Fk is equal to 140. And if you did that, I think one of these answers is 140 over 200. But that would not be right, okay, because this thing is accelerating. In step 3, for this one, I would have to say the sum of the forces in the x direction is equal to max, or 140 minus Fk is equal to 20 times ax, and ax is equal to 5. I'm just going to erase that and put in 5. And then I solve this for Fk. It's 140 minus 100, or 40 newtons. And so Fk is 40, so I can put in 40 right there. And my mu is going to be 40 over 200, or 0.2. That's 20 over 100, or 20 hundredths. Okay? That's another great problem. By now, I hope that you're seeing these and you can do these. Could you do these on your own? Some of you can, some of you can't. It's not too late. With practice, we can still get them, okay? I know that you can. I want to warn you again. This is what, the easiest exam that you'll have all semester? No, it's the hardest exam, I think, in past experience, that students tend to do the worst on this exam than all the other 3. So I know some of you didn't do well in the first exam, like, oh, I can't do any worse than that. That's not true. You know, you're beginning to build your skills, and so you can do better. I just want to warn you about that. I don't want to stress you out. Have I stressed you out? I want to stretch you out a little bit, okay? Just enough to get you going in the right direction. Okay, let's do number 19. You're going to have one like number 19. Hopefully this one is a little bit easier. I'll just let you read it for a sec, and maybe you can tell me what the answer is. This is a 500 kilogram block. So if it were just sitting there, hanging by a rope, it would have a force of 5,000 newtons. But this one is not just sitting there. It's descending at a rate of 2 meters per second squared. So what is the tension in the rope? No, be careful. You're thinking in the right direction. Is that if this thing is descending, is the tension in the rope going to be more or less than the weight of the object? It's descending, it's going down. going to be more or less than the weight of the object? It's going to be less. But we've done this problem where I have an object hanging in an elevator like that. If I say the sum of the forces in the y, I have Ft, that's the tension, Fw. The sum of those is Ft minus Fw equals Ma. And because A is negative, that means that the tension is going to be less than the weight. Yeah, Jenna, right? Absolutely. Yeah, you can automatically rule out D and E. In fact, then you could probably pretty much guess that it's going to be A, right? And you would be right that it is A, in fact. I can see that because I got this 500 times 2 is 1,000. So I actually know it's going to be 1,000 newtons less than the force. Let's go through the process, okay? Because if you don't see that, which you probably don't, you just have to go through the process. Draw the vectors, resolve the vectors. Don't have to do that here. Apply Newton's second law, and then solve the equation. This is the application of Newton's second law right here. If I want to find the tension, I say the tension is equal to Fw plus Ma. But the acceleration is down, so that means it's going to be 1,000 plus 500 times negative 2. So that acceleration is negative. This should be 5,000, I'm sorry. 5,000 plus negative 1,000, that's equal to 4,000 newtons. I mean, you have a problem that's almost identical. It's just different numbers. Yeah. Oh, the 5,000, the mass is 500 kilograms, and so the weight is 500 times 10. Right? Yeah, often you have to find the weight of the object, and you just have to know that you multiply that times 10. Okay? There's more? All right, let's do a conceptual question. You'll have those too, of course, so let's think about that. Ooh, let's look at number 18. I have this object that slides down an inclined plane, as in this figure, and a frictional force acts upon the object. So let's see which of these statements are true. As you know, well, it looks like statement 1 has to be true because it's in every option. And in fact, the frictional force is up the inclined plane. That is true. The frictional force opposes the direction of motion. This thing's moving down, so the frictional force is up. But you see it's in every one. The frictional force depends on the mass of the object. Is that true? We know the frictional force is dependent upon mu and the normal force. Does the mass affect either of those, either mu or the normal force? Does it? Does the mass? It doesn't impact mu. That's just the material. Does it impact the normal force? Is the normal force dependent in some way on the mass of the object? Yeah.
So can we always say that the normal force is the opposite of the weight of the object?
We can't always say that the normal force is opposite the weight. And in fact, in this
one, it's going to be
right. However, we can say that the normal force in this case is related to the weight. In fact, we know if we break this weight into its two components, this is going to be Fw sine of not theta, but 90 minus theta. I'll call that phi. Or as y'all call it, phi. Right? I'll call it phi. Okay. So, is the normal force dependent upon the mass in this case? Yes, it is. So, it has 1 and 2 are both correct. If theta increases for this moving object, the frictional force will always decrease. Ooh, this is tricky. Will the frictional force decrease if I increase theta? I don't want to get into that. Let's not talk about that right now, okay? That's kind of a trickier thing. We had talked about it in that class, but we'll just leave it right there as 1 and 2 are correct, okay? Don't sweat number 3. All right, we move on? All right, I don't want to get in the weeds too much. Okay, let's look at number 22. 60-kilogram swimmer pushes on the pool wall and accelerates at 4 meters per second squared. The friction experienced by the swimmer is 100 newtons. What is the magnitude of the force that the swimmer applies on the wall? Okay, we're going to follow the same steps. I draw my swimmer. This is how I feel when I swim. I feel like a big block moving through the water. Y'all feel that way? Like I move really slowly through the water? No, you're like fish, aren't you? So I have a frictional force that is 100 newtons. That's like the water pushing on you. And then the other force is you pushing on the wall. So that's F. I know that I accelerate in this direction with an acceleration of 4 meters per second squared, and I have a mass of 60 kilograms. And I just want to know, what is the force? I drew all the forces. I labeled my acceleration 2 in this case. Now I'm going to apply Newton's second law. F minus 100, F minus 100 is equal to the mass times acceleration. That's going to be 60 times 4, or 240. And so F has to equal 340 newtons. Okay? Let's do number 24. It's a good conceptual question. You have 3 equal masses. So I have M, M, and M. And if I apply a force to one of them, F, then it causes an acceleration A. And now I want to know, what if I combine all these 3 masses, what's going to be my new acceleration? So you can think of it now as having the same force, F, but now applied to a mass 3M. I like these kinds of questions. You'll see them in the concept tests a lot, so go back and review those concept tests there on Moodle. But I know that F is equal to M times A. And so the way I like to think of it is, well, what if I triple the mass, I keep the force constant, what's going to happen to my acceleration? Will it go up or down? Does the acceleration on this bigger mass, is it bigger or smaller than the acceleration on the smaller mass? It's smaller, right? Like I can thump a fly and it goes flying across the room. I don't know why you'd thump a fly. Or I can thump a car and it doesn't move anywhere, right? Because it has such a bigger mass. So if I increase the mass, that means the acceleration decreases, and it has to decrease by a factor of 3. So the answer here is going to be C, that it's A over 3. $25 is another good one. In fact, I think 25 is part of a bigger problem. No, it's not, but you could see it as part of a bigger problem. I have this guy pulling this block, and I ask, what is the normal force? And then after that, let's find what is the acceleration of this object. So, follow my 4 steps. Draw the forces. I have my normal force. I have my weight. I have this force, which is 40 newtons. And then I also have my kinetic frictional force. You might be inclined to say that the normal force is equal to the weight, because the normal force looks like it is, but don't forget that you have this vector too. That's off axis, so it has an x component and it also has a y component. So I would say go into step 2, which is to resolve your vectors. Fn, F sine of 30, F cosine of 30, Fk, and then Fw. So now you see, once you resolve your vectors, if I apply Newton's second law, sum of the forces in the y, is equal to 0 because it's not accelerating in the y direction. So I don't write may because ay is equal to 0. That's going to be f sine 30 plus fn minus fw is equal to 0. So fn will equal to fw minus that f sine 30. Because, you know, like this desk has a weight of 400 newtons. If I pull up on it with a force of 200 newtons, now the normal force is no longer 400 newtons. It's less, right? It's 200 newtons. It's less by whatever amount I'm pulling up on it. And that's what's happening here. I'm pulling up on this block, and that means that the normal force is going to be smaller. By the way, is the friction going to be smaller or bigger than if the person was just pulling in this direction? Here, repeat that. So if I'm not pulling up like this, but instead I'm pulling horizontally, is the frictional force bigger or smaller? Yeah, if I'm pulling horizontally or up, which is bigger? Horizontal, right. So if I'm pulling horizontally, that means my normal force is bigger. That means my frictional force is bigger. What if I'm pushing it this way? The frictional force is bigger or smaller than the horizontal frictional force? Let me repeat that. So if I'm pushing it like this, in a downward motion like that, is my frictional force bigger or smaller than if I was pushing horizontally? Bigger, because my normal force is now gone up, and that's increased my frictional force. Which begs the question, when you go to the grocery store, how do you push your grocery cart? You push it like this all the time, right? Like, I don't know why we don't pull it behind us like this, because then we have less friction acting on the cart. It just makes you think, right? Like, I feel like somebody has tricked us into pushing our carts in that way. But you don't have to succumb to the machine. Next time you go to the grocery store, you just pull your grocery cart behind you. If anybody says anything, you just tell them, this decreases the normal force of the cart, and then I have less friction. It's just better. Okay? So you go to the grocery store, you can do that. So then our Fn then is 110. That's my weight. 11 times 10 minus 40 sine of 30. All right. I think that's 90, right? Is that 90? Pretty sure it's 90. What is the acceleration? Let's go ahead and find the acceleration. So to find the acceleration, I'm going to do the sum of the forces in the x direction. And the sum of the forces in the x direction are f cosine 30 minus fk equals max. And then I solve that. However, I don't know fk, but I do know fn. So I can figure out fk because mu is 0.1. Fk then is equal to 0.1 times 90, or 9 newtons. So over here, I have f 40 cosine of 30 minus 9 divided by the mass, which is 11 kilograms. That will be my acceleration in the x direction. You could, actually, I'm pretty sure you will see a problem like that on Friday. They're common. You can go through and look in the old test and see other examples of that. Okay? Let's do a few projectile motions. We can come back if we have time at the end and do some more inclined plane problems. Because you're going to see 1, 2, 3, I think, calculations with an inclined plane, and then a couple other conceptual questions for the inclined plane. But you're going to see a lot of projectile motion. So let's go do that, huh, Jenna? Got some projectile motion? All right. Looks like we've done a lot of these, so why don't we go up 1, the fall 17 exam. Look, you're going to have a question like 1 and 2. I'm going to give you a question where you just have beginning level, end at the same level as it started, and I ask you something about the maximum height, the range, or the total time in air, or the time that it takes to get up to the top. So just be prepared for those. Fortunately, these aren't that difficult, right? If you mastered chapter 2, if you know how to do those free fall questions, the problem they go up and down, and these are just really a lot like those questions. I draw a picture first. I want to know how long does it take to get up here? That's what this question is asking. I know that it has an initial speed of 40 meters per second. And I also know that that's broken into an x and a y component. There's the x, there's the y component of the velocity. I know that that y velocity decreases, decreases, decreases until it gets to the top, and then it stops in the y direction. It still has an x velocity, but it has no y velocity. So I can use that fact to find out the time at the top. I know that Vy at the top is equal to 0. I know that V naught y is 40 sine of 30. That's the y component of my initial velocity, minus 10 times t. So that's going to be t is equal to 2 seconds. C. And then next, I want to know what is the horizontal range of the object. That means I want to know what is the position when it gets here. I know that x is equal to Vx times t. Be careful, we're not using the 2 seconds here because we want the time down here. I know if this is 2 seconds, what is the time at the end of the trajectory? It's 4 seconds. So I'm going to have that. It'll be Vx, which is going to be 40 sine of 30, plus, oh wait, no, I'm sorry, times t, which is 4 seconds. So it's 160 sine 30. Yeah, you're right. Thank you. I'll fix it. I get 140. So this should be cosine, and that's equal to 140 meters. Okay, there'll be other problems here, like what is the x component of the initial velocity? But look, you've already found that. You found it right here, that 40 cosine 30. So you can find the answer there. It's 35 meters per second. All right. Let's look at a conceptual question like number 5. Definitely going to have a question like 1, 2, and or 3. A couple questions like that. Number 5 asks, for the two-dimensional motion of a projectile that begins and ends at the same height, all of the following apply except which of these? The y component of the velocity changes direction during flight. True? Is that a true statement? Remember, the y velocity starts out big, gets smaller, goes to 0, goes negative, and gets bigger in the negative direction. Does it change direction during the flight? Yes, it does change. That's true. So that's not our answer. The y component of the acceleration is always negative. Yes, always negative 10. Ay is always negative 10. Even up here, where it's equal to 0, where it has 0 velocity, the acceleration is still negative 10. The maximum speed is at the top of the trajectory? No. The maximum speed is actually where? At the very beginning or at the very end. That's where you have your maximum speed, because your y velocity is the maximum, and your x velocity is there. At the top, all you have is the x velocity, which doesn't change. So this one is not correct, which means it is the answer. And the time in flight is determined by the y component of the velocity. True? We know it is true now, but that is true. that the amount of time that you spend in the air is dependent upon the y component of your velocity. If your y component is bigger, that means it's going to go up farther and stay in the air for a longer amount of time. All right. You're going to see too, shouldn't be a big surprise, a problem like number 6. We've done this in lab. This is where you shoot something off horizontally. You hit a ball horizontally from top of a cliff. It's 20 meters tall. What is the horizontal range of the ball? I could ask a couple of things of this, like this. Like I could ask, what is the y velocity at the end of the trajectory? I could ask, how long does it take to fall through, or how long does it take to reach the end of the trajectory? I could ask several questions and be prepared for any one of those, but you'll definitely see this scenario where I have an object that follows a path like that. I might give you the initial velocity, or I might not. But I would give you, if I didn't give you the initial velocity, I'd give you the x and y directions, just like you did in lab. So here I give you that. I want to know x. I know that x is equal to vx times t. So to find x, I need to know vx and I need to know t. I know vx. That's what this 5 meters per second is. So I need to find t. And remember, when I'm finding t, it's just I'm thinking about just dropping an object, and I want to know how long does it take to fall that distance. In this case, that distance is 20 meters. So if I imagine an object at 20 meters high, how long does it take to cover that distance? I would say y is equal to v naught y t plus 1/2 ayt squared. Fortunately, v naught y is 0. So that term goes away. Otherwise, I have to use the quadratic to solve this. Y is negative 20 equals 1/2 negative 10 t squared. So t is equal to square root of 4, or 2 seconds. It takes 2 seconds to get here. And that could be the question too. I could ask you, what is v naught, or how long does it take to reach that? But then if I want to know the horizontal range, I come back here and I get 5 meters per second. At 2 seconds, that's going to be 10 meters. Another question that I could ask is, what is the speed of the ball at the end of the trajectory? Think about in your head how you would go about that. I already know the x component of that speed, but I know now also at the end that it has a y component. And so I have to find out what is the y component at the end of the trajectory. As I know, again, that the x component is constant throughout the motion. However, the y component starts out at 0, and it gets bigger and bigger. And so if I asked you what is the velocity at the end of the trajectory, what you have to do is figure out the y component of the velocity. That would be 0 is the initial velocity minus 10 times 2 seconds. I got this 2 seconds. I know that it's 2 seconds right here. And so that's minus 20 meters per second. So at the end of the trajectory, I have an x component that's 5 meters per second and a y component that's minus 20 meters per second. And if I want to know the speed of that object, Pythagorean theorem, I would say the square root of 5 squared plus 20 squared. 400, square root of 425, whatever that is. That's, okay, just a second, Alan. That's why this test is hard, because it takes everything that we've learned up to this point, especially that trig and the vector stuff that we did in chapter 3, and it puts it all together. Alan?
When you're finding like the halfway point, use the dy, like the shorter dy equation, and when you're trying to find the whole point, use the longer equation.
Yeah, I think I understand what you're asking. I think you're asking about this problem up here. that on this problem, when I'm looking for the halfway point, you call it, which I call it the top of the trajectory. It is the halfway point. That I'm using the fact that here, the Vy is equal to 0. I know that. That's a set point in this trajectory to me that I know something about. And so I say Vy is equal to V naught Y plus AYT. And so I know that's 0. So I have some information for that, and I can solve this. But if I'm thinking about the displacement, and that's what I was doing here, to find the time here, I know something about the displacement. I know that it's starting 20 meters above the ground. And I know the acceleration, so all I don't know is t. And so yeah, I can solve this for t. So yeah, you're right. You know, a good practice is on your scratch paper, as soon as you get it, write down the equation. There are only 3 equations, right? There's the 2 kinematics equations, and there's F equals ma. You probably need to write down F equals ma. But write down those kinematics equations, make sure you got them right, and then you can use them throughout. Now remember, with projectile motion, we had some variations of those. I'll just write them down to remind you that I had y equals v naught y t plus 1/2 ayt squared. And then I also had vy equals v naught y plus ayt. All right, those are just our kinematics equations. And then I have x, similar. X equals v naught xt plus 1/2 axt squared. And Vx equals V naught x plus AXT, but AX in both cases here is 0, so those go away. So those x equations are a lot simpler. Really, with x, we only have x is equal to Vx times t, because in fact, V naught is the same as Vx. So I can rewrite those x equations as simply x equals Vxt. I would write those on your paper as soon as you get them, as soon as you start. Please don't write it beforehand, just because you know y'all should all know these equations by now anyway. And then just have them there on the side of your work area that you can refer to them. Okay? It'll save you a lot of grief. Do some more? Is this too fast? Okay, hopefully it's not too fast. Like hopefully you're tracking along with me. If you're feeling lost, you should probably come see me. We'll help. I'll help. I will say that the tutoring center is really great. We have some great tutors over there. Jake Knockan, I think Adela Guidros is over there. Is that right? She's really good. She did really well in this class. Autumn Andres, is she still there? No. Tutoring center is really good, and it's cheap too. A good tutor would be $30 an hour, and the tutoring center here is only $25 for the semester, and that covers your organic, your physics, your calculus, covers all those difficult courses. All right, let's do this one. Which of these statements is true for an object in projectile motion? The x component of the velocity does not change. True? Yeah, that's a true statement. Yes, it's constant throughout. The y component of the velocity is 0 at the top of the trajectory. True? Yes, true. The velocity is greatest at the beginning of the trajectory. True? Yes, because the y component of the velocity is the biggest there. The x component is the same all throughout. So yeah, true. The acceleration in the y direction at the top of the trajectory is 0. Not true. Thank you. So it's going to be A is the right answer. Work those problems just like that. Just go through each statement and ask, is this a true statement or not? And if it is, just cross it off. And notice also as I go through them, I don't think that these are harder to pick out wrong answers. I mean, you could have said, yeah, just you have to go through them all. Don't forget that you're probably going to see a question like this, so it's not going to be just like this. It could be displacement or velocity, either way. It could be x or y. But don't forget how projectile motion looks in these different graphs. I can draw them for you. So if I have, this is an object that's launched horizontally, so the y velocity initially is 0, and then it gets bigger in the negative direction. Which of these starts out with a small slope and ends with a big negative slope? That would be C is right. Starts with a small slope, ends with a big negative slope. If I were to plot x versus t, it has a constant velocity, so it's going to look like that. The slope of that graph does not change. It has a constant positive velocity in the x direction. If I were to plot Vy versus t, it would look like this. And if I were to plot Vx versus t, think about what it might look like in your head. I know that it has a constant slope. The slope doesn't change. The slope is the velocity. That means the velocity doesn't change. So it's going to look like that. A constant velocity at one value, not changing. So be able to identify those for all the different parts of projectile motion. You're going to have a problem similar to number 11 as well. You fire a ball with an initial speed of 20 meters per second, an angle of 30 degrees from the horizontal. It lands on a table 26 meters from the original position at t equal 1.5 seconds. What is the height of this table? This looks complicated, but because I give you the time, it's not. It's not a complicated problem, even though it seems complicated. And the reason it's not is because I give you the time. The time, that's like most of the effort you have to put.
You're never going to require us to use a quadratic equation.
No, I'll never require you to use the quadratic. Not on an exam. You have to do that in lab, but it's so tedious. I mean, I often make mistakes with the quadratic. It's just not, you can't do it quickly enough. All right, so I'm firing this like this, and it lands at some height. And I want to know what is this height. Because I give you the time, I can just say y is equal to v naught yt plus 1/2 ayt squared. And it's really just a matter of plugging in the values. So this is going to be 20 sine of 30. That's the y component of the velocity. That should be second nature to you by now. Times t, which is 1.5, minus 5, 1.5 squared. The minus 5 is 1/2 of -10. You're right, though, if you had to find the time, this is a lot like what y'all did in lab. If you had to find the time, you'd have to use the quadratic formula to solve for t, if you know why. Okay? Expect a problem like that. You have 4 or 5 different calculation problems for projectile motion. Or no, more than that, I think. 6 or 7. Let's go back. We'll do some other conceptual questions. Number 9, right here. From the same height and at the same time, a ball is fired out to the side, and another ball just drops to the ground. Which one will hit the ground first? The drop, or they both hit at the same time? Same time is right. They're going to both hit at the same time. That's a very important fact about projectile motion, that they'll both hit at the same time. What if, it's going to rock your world, what if I have an object, hold on, let me make sure this is right. No, never mind. All right. How about number 4? Which of these statements is true? Do each of these have different angles? Number 1 and number 2, they have different angles? Yeah, they have different angles. Number 2 is a steeper angle. They have different initial speeds. Yeah, not necessarily. So we're going to do 2 on that. And then Shell 1 is in flight for more time than shell number 2. Yeah, so that's not true. Shell number 1 is actually in flight for less time. So the answer would be 1. Okay. Yeah. All right. What else? Have any particular problems you want to work through? Flip through your exams in the back. What do you want to see if you can work through? Otherwise, I'll just go work through something. Did we do incline planes? You want to do incline planes? Yes. Okay, let's do incline planes. We have 10 minutes. So, all right, 10 minutes or 5? Ah, shoot. All right. Incline planes are important. Okay, we've been doing them for a week or so. You're going to have a problem like this where I give you a set of equations and you have to figure out which one's correct or not. I recommend that you just write out the equations, or you can probably look at them after you draw the vectors. Well, let's just do it. So here I have a normal force in this direction. I have the block is accelerating, and there is a kinetic frictional force. So my kinetic frictional force is in that direction. And then I have a weight. I'm going to go and resolve my weight into its 2 components. So I'm skipping straight ahead to step number 2. This is going to be FW sine of 30. I take 90 minus 60. And this is FW cosine of 30. And then I can look at these equations and see which one is correct or not. All right, number 1 is not correct because it should be Fn minus FW sine of 30. Number 2 is not correct either because it should be minus Fk plus Fw cosine 30 equals MAX. And then number 3 is not correct either because it should be Fn minus Fw sine of 30 equals to 0. So in this case, none of these are correct. Just go through each equation and look for the mistake or look to see if that equation is correct. But I would draw your vectors just like I've done here, your resolved vectors. Usually, those resolved vectors will help you in another problem. So you'll see a similar situation in another problem. Maybe you can use that work. Let's do this one. This one, there's no friction acting on this. And then we'll look at 25 and 26. I want to know what is the acceleration down the block. So I'm going to draw my coordinate system. I'm going to skip ahead and resolve those vectors. So I have Fn, I have Fw sine of my 90 minus angle, or 60 degrees. This is Fw cosine. So those are all the forces that are acting on it. If I want to know the acceleration, I say the sum of the forces in the x direction equals MAX. The forces are only Fw cosine 60 equals MAX. That's going to be 10 cosine of 60. So 5 divided by 1 equals AX. 1 is the mass. This is equal to 1. So 5 meters per second squared. Let's look at the next problem, and that's what you'll have. Tristan.
The way that you subtracted the angle to be at 60 was confusing.
So remember, I have an inclined plane. And I have a force weight acting down. This is the angle that I give you. In this case, I gave you 30 degrees, but this is the angle that you want. So you'll always do 90 minus the angle. That's always. Don't even ask a question. You always take that angle, 90 minus that angle on inclined planes. I want to throw in the friction, okay? Can I have 30 more seconds? Because you'll have one like this. If I have friction, Fk, like that, I want to know now what is the acceleration, I think. Yeah, what is the acceleration? I have to first find out the normal force, which is going to be Fw, which is 10 sine of 60, or 8.7. Then I have to find Fk, which is going to be mu times the normal force. That's 0.12 times 8.7, which is 1 equal to 1 Newton. And then I can do this sum of the forces in the x direction again, but now it's going to be different. It's going to be FW, I'm going to change my signs. Cosine 60 minus FK equals MAX. And then I can solve that for AX. We're out of time now, so we'll finish that one up. You can look in the old test on the exam videos. You'll see something like that one. Okay? Let me just say that if you miss the exam, there is a penalty of 15 points if you miss the exam. That's off the top. And then there's another penalty for every day if you do not contact it. So it's in your best interest to take the exam at this time that it's given, or there's a 15-point penalty. Okay? Y'all have a great day. I will we'll have a help session tomorrow at 1 p.m. It's raining out here. You can head that door. It's raining. You can head out that door if you want. It's raining, yeah.